Here are a few examples that we'll work through that have the different notations. So the lowercase c for cosine and capital C. So when we want to find inverse cosine of 1, what we want to do is we want to think the cosine of what number or numbers equals 1. That's what this statement right here is asking. The cosine of what number or numbers equals 1. Well, we know that the cosine of 0 is equal to 1. So I'm going to try to sketch a quick graph of cosine. You don't have to do this. I'm just showing you something that we can think about here. So cosine starts up at 1, it comes down, goes down to -1, back up to 1, and it just continues this sine wave over and over and over again. It also goes to the left of the y-axis. And so we see that cosine hits 1 4 times in our figure, but it hits it infinite times. So we want those values. Well, we know that the period of cosine is 2 pi, and so the inverse cosine of 1 is equal to 0, 2 pi, 4 pi, 6 pi, it keeps going, dot, dot, dot. We also know that it goes in the other direction as well. So I'm moving this over because we can actually put that -2 pi is a solution and -4 pi, and we'll put dot, dot, dot in this direction. Well, there's a better way to write that, and that's what we want to do here. So inverse cosine of 1, using this lowercase c, because it's asking for all solutions, is, we might say, like start with 0 because that's our first one. So I'm going to write that just so we have that idea down, but 0 plus 2 pi k, where k is an integer. But we really don't need the 0. We can just write 2 pi k, where k is an integer. And so that's the solution to that one. When we come over this next question right next to it, it has the capital C inverse cosine. So we recall that when we have a capital C, we only want answers from 0 to pi. And so, and the reason we want answers between 0 and pi, that's when we have a function that's 1 to 1. So there, you'll only ever get one solution, or possibly no solutions, when you have a capital letter here for your trig function. So in this interval, when does inverse cosine equal 1? Well, it's at 0. And that's the answer for that. So it limits it to just one answer, because when we talk about inverse cosine with a capital C, it's referring to a 1-to-1 function. Well, we can do something similar here as we move down to inverse sine of root 2 over 2. We should know that inverse sine of root 2 over 2 is pi over 4. And we also remember that sine is positive. Remember, we use our little all students take calculus. Sine is positive in the second quadrant as well. So you have another solution of 3 pi over 4. And the pattern will keep repeating. Sine has a period of 2 pi. So we can take each solution here and add 2 pi to it to get another solution. And so instead of thinking 2 pi, we'll get a common denominator that's 8 pi over 4. And so what's pi over 4 plus 8 pi over 4? That's 9 pi over 4. And then We can do the same thing with this one. We're at 3 pi over 4, add 8 pi over 4, which is the period of sine, and we get 11 pi over 4. And again, we can actually continue doing that again. We'll take this one, and we can add 8 pi over 4. And we get 17 pi over 4. And we can continue over and over and over again. We also, which again, I didn't leave myself room, we could subtract 2 pi, which is 8 pi over 4. And that would give us negative 7 pi over 4 as another solution. Again, you don't have to write all these solutions. I'm just showing you the idea behind it. Here is our graph of sine. It starts at 0, 0. There's one cycle, another cycle, and it also goes in this direction. So where are these pi over 4s, or this root 2 over 2? Well, it's about here, here, and here, and here, and it just keeps continuing over and over and over again. So there's going to be an infinite number of solutions. And so it kind of looks like they come in these, well, here's our first cycle to right here, and there's 2 solutions in there. And then, so these 2 first red solutions I'm enlarging, you can add 2 pi to each of those to get each of those blue solutions, and then you can add 2 pi to those to get these next 2 solutions, these green ones. And so the way we can write this is inverse sine of root 2 over 2 is, and we'll start really just with the ones in the first, which match up with these right here in that first period. We will write pi over 4 plus 2 pi k, because that gets us to this one and then to the next one. So that's part of it, and then we can write 3 pi over 4 plus 2 pi k, where, put a semicolon here, k is an integer. Now we come to this question right across from it, this one with a capital S, and this, remember, this is a little different than cosine. This time we're looking for answers between negative pi over 2 and pi over 2. And again, when we have this restriction here, it's just 1 to 1, so we will only get one solution. So what is the only solution in that interval? Well, it's going to be our very first answer here. It's going to be the pi over 4. Notice if we tried the 3 pi over 4, 3 pi over 4 does not fit in the interval. And none of those other answers fit inside the interval. So when you have the capital S, it's just one solution. All right. Moving on to this next example. This one is different because, for a couple different reasons. Sine of inverse cosine of 4/7. Well, this, if we think back to what I mentioned before, well, it's a capital C, so it's only looking for one solution. And way up here, I said when we see something like an inverse cosine, it's like the cosine of what number, maybe I should have said what angle, represented by a number, equals. The cosine of what angle equals 1. I should have put that in there. All right, so we're looking for an angle there. So when we come down here, this part that I'm underlining here, this is actually just an angle. That's an angle. We'll call it theta. And so what we do for these, like 4/7 isn't one that we're familiar with. It's not a root 3 over 2 or a 1/2 or a root 3 over 3 or something like that. So what we do is we think we're going to draw a triangle. We think, all right, well, I want the cosine of some angle to be 4/7. Well, 4/7, and when we're dealing with cosine, this is going to be the adjacent side. So all the way back to our definition over the hypotenuse. So our adjacent side is 4, our hypotenuse is 7, and we want the sine of this angle. All right, so in order to find sine of that angle, we need to find the opposite side. So again, this part right here I'm circling just represents an angle. It represents an angle. So here's the angle right here, whose cosine is 4/7. So I put 4 in for the adjacent, 7 for the hypotenuse. But in reality, or like the final answer, I want the sine of that angle. Well, sine is opposite over hypotenuse, so I need to find this opposite side here. I'll just call it A. So we can say A squared plus 4 squared is equal to 7 squared. Subtract 16 from both sides, and we get 33. So A equals the square root of 33. And so the sine of this angle is equal to opposite, so root 33 over 4. And so since theta was just represented by this section I keep highlighting with circles and underlines, we can say the sine of capital C, so inverse cosine of 4/7 is root 33 over 4. Okay, this one I feel like it's a little out of order. We just did that more difficult one, but this says find the cosine. I think this is supposed to say inverse cosine of negative root 2 over 2. Well, when we have inverse cosine with a capital C, we only are looking for 1-to-1, so we're looking between 0 and pi. Well, cosine equals positive root 2 over 2 at pi over 4, but we need it to be negative root 2 over 2. And so we know that sine is positive in the second quadrant, but cosine is negative. So this is going to equal not the positive part, not pi over 4, but 3 pi over 4, which is in the second quadrant, which does fit inside our restricted interval. All right, that's it.